In this interactive simulation, we're generating the Langmuir isotherms where we have a binary mixture. What this means is that the absorption of one molecule is going to affect the absorption of another molecule. So we have a simple Langmuir isotherm where the denominator term in the isotherm has the partial pressure of each component. So we can plot the number of molecules absorbed per sites on the surface as a function of the total pressure. So this pressure of A plus the pressure of B. So we raise the temperature, the amount absorbed is going to decrease. So we can change the heat of absorption of A, heat of absorption of B. Notice the heat of absorption of A is higher here, and therefore we have more A absorbed in B. The pressure of B is higher than the pressure of A, but the heat of absorption more than compensates for that, and that's why more A is absorbed. We can also change how many sites a given molecule needs. For example, a bigger molecule might occupy more sites, like 2 sites, compared to a smaller molecule that might occupy 1 site. And the value of looking at this is to understand, for example, during a catalytic reaction where we have more than one component competing for sites, if A and B are reacting with each other, and we're conditions where we have mostly A on the surface, reaction will be very low. And so Langmuir isotherm is the simplest model for absorption, but hopefully this gives you an idea of behavior and things you should think about when you're looking at absorption for separations or for catalytic reactions. And so let's look at this interactive simulation and see how the amounts absorbed change with these various parameters that we can change. So here's the interactive simulation, and you can see as we raise the temperature by moving the slider, then the coverage goes down significantly. If I raise the heat of absorption of A, then you notice that it doesn't take a huge difference, 15 kilojoules per mole, and essentially the surface is covered with A in a mixture. Likewise, if I lower the heat of absorption below that of B, then I have the reverse, that now only a 6 kilojoule per mole difference, and we have almost exclusively B. Now the pressure of B is higher. If I go to where the heat of absorptions are about the same, and then I increase the pressure of B, well then amount of B absorbed increases, amount of A decreases. Change in number of sites, so more sites required for B, then the loading of B goes down. There are just less sites available on the surface. And so by manipulating these parameters, hopefully you get a better feel of what's going to be absorbed on a surface and how dramatically the amounts absorbed depend in particular on the heat of absorption, but also on temperature. I can raise the temperature and the coverage goes to 0. I essentially have desorbed everything. The desorption rate is so much higher than the rate of adsorption.